Good evening, sir, madam. I am Ankur. I am presenting my ELP101 project, and my entry number is 2021 PH 10841. My topic is resonance. The definition of resonance is when the natural frequency of a circuit becomes equal to the frequency of LC oscillations, the whole circuit becomes purely resistive and the current attains its peak, which is the maximum value, then this is called a resonance in the RLC circuit. We can see the resonance in our nature in various forms. As we can see in the guitar, the resonance takes place, then it attains a maximum value, then vibrations of the strings is you obtain a high pitch sound. In the second picture, we are looking at a man who is matching his frequency with the natural frequency of the glass in the glass drop. In the third application, we find the oven. The resonance can cause the heating quickly because the atoms having its natural frequency. When the frequency of the electromagnetic waves become equal to the natural frequency of the particles of food, the resonance takes place and the heating causes quickly as heat produced. As the fourth applications is radio. Radio is a majorly very famous, and here we adjust the natural frequency of the receiver and to match the natural frequency to with the resonance frequency. Then the resonance takes place and we hear a clear and a high pitched sound. Here it is a circuit diagram of series RLC circuit where R is resistor, L is inductor, and C is capacitor. And these are connected to a AC source of amplitude Vm and angle phi. Here we can find the impedance of the circuit, which is R plus ZX. Here real part is a resistance and imaginary part is the reactance, and we expand it is equal to Z equal to R plus Z times omega L minus 1 by omega C, where omega is our angular frequency. The resonance takes place when the imaginary part becomes zero, which implies our reactance becomes zero. Then the impedance becomes equal to resistance, which is the minimum value of the impedance at resonance. And the current flowing through the circuit increases as the impedance reduces to the its minimum value, which is the resistance. Then I max is equal to V by R. Then current become maximum at resonance. Here we make the imaginary part of the impedance equal to zero. Then XL is equal to XC. Means we equate the reactance inductive reactance to the capacitive reactance. Then we get a formula omega R is equal to 1 by root LC. Here I'm showing the phasor diagram. In the first case A, inductive reactance is smaller than the capacitive reactance, which is for the below resonance frequency. Then we obtain a Z at an angle phi, which is lagging. In the second case B, at resonance frequency. At this step, inductive reactance is equal to the capacitive reactance. Then in this case, the impedance becomes equal to the resistance and they are in same phase. In this third case, C, the above resonance frequency. In this case, the inductive reactance is greater than the capacitive reactance. Here, the Z is leading by the resistance by angle of phi. Here, omega naught is the resonance frequency as we show in the graph between current versus frequency, then we find a very certain one frequency omega naught where current is maximum in this case, and omega 1 and omega 2 two frequencies where the current is 70.7% of the maximum value. Here I am defining a term bandwidth. Bandwidth is measured as the amount of data that can be transferred from one point to another in a specific amount of time. In this graph, we find the bandwidth is omega 2 minus omega 1, and we can say that it is the bandwidth. Here we define the quality factor, which can be say it is the sharpness of the graph we made earlier. Here I made a graph. Then this quality factor makes the sharpness of this graph. Quality factor determines the sharpness. It relates to the maximum peak energy stored in the circuit to the energy dissipated during each cycle of oscillation. It is equal to the ratio of resonance frequency to the bandwidth. Quality factor, when we derive, this is equal to the resonance frequency divided by the bandwidth, or we can say that power stored divided by power loss. In general, we obtain a relation quality factor is equal to 1 by R root L by C. And where I have described the series, similarly, the parallel resonance circuit looks like that. The resistance, inductor, and the capacitor are in the parallel, and AC source is connected to them, and these three elements are at the same potential. Here impedance we can derive 1 by Z equal to 1 by R plus 1 by Z omega L plus J omega C. Then 1 by Z is equal to Y, means Y is here admittance, and 1 by R is equal to G, which is the conductance. Then Y equal to G plus J times omega C minus 1 by omega L. At the resonance, similar as in the case of series, in the parallel also, omega C is equal to 1 by omega L. Here conductance become maximum. There we receive the same resonance frequency, which is equal to omega R equal to 1 by root LC. Implies at resonance, the admittance is equal to the conductance. Implies that Z impedance become minimum and the current will flow through the resistor only. Here we can describe also the quality factor. In the case of parallel RLC circuit, quality factor is also called the current magnification. While in case of series RLC circuit, quality factor is also called a voltage magnification. In this case, we receive a quality factor is equal to R under root C by L. Thank you. And my presentation is done. Thank you all of you.